Okay, so in this video we're going to look at the law of sines. This is a very important tool. Along with the law of cosines, it allows us to learn things about triangles that don't have any right angles in them. So it allows us to solve these triangles, as we say. If we have some combination of sides and angles, we can solve the thing, which means we can fill in the rest of them. And most triangles, well, I don't know what most would mean, but Okay, so in this video, we're going to look at the law of sines. This is a very important, very fundamental thing that you need to know. This, along with the law of cosines, allows us to learn things about triangles that don't have any right angles in them. So triangles like this one, if we have some combination of sides and angles, but not all of them, we want to be able to solve the triangle, as we say. We want to be able to fill in the rest of them. And depending on what combination of sides and angles you have, you can either use the law of sines or the law of cosines to fill, or both of them to fill in the rest. And so it's important to know both. So in this one, we're going to look at actually the proof of the law of sines, where it comes from, and the actual proof is not so important as it's always nice to prove things, but the really important thing is to notice that you can do stuff like this, that you can. Okay, so in this video we're going to look at the law of sines. This is a very important, very fundamental thing that you need to know. Along with the law of cosines, it allows us to solve, that is, to fill in the missing sides and angles of triangles that don't have any right angles in them. So triangles like this one. If we know some combination of the sides and angles, but we don't know all of them, we can use either the law of sines or the law of cosines, depending on which combination we're given in the problem, to fill in the rest. We call that solving the triangle. So really important to know both, and we are going to look at the law of sines here. We're going to prove it, and we're going to use it. We're going to see how it could be used. The proof, although not strictly necessary to know, it's always good to know how to prove things. I really like showing this and the law of cosines proof because it introduces you to this really important technique of drawing right triangles into things. So the law of sines and cosines are used on non-right triangles, but in order to prove them, we actually use the Pythagorean theorem, right? When you don't have a right angle, you can't use the Pythagorean theorem. But very often you can draw in a right angle. You can make a right angle where there wasn't one. And that is the way that we prove this, and that's a really, really, really important thing to know that you can do, an important thing to see as early on as possible. So that's why we're going to look at the proof presently. So, all right. First of all, what does the law of sines say? Well, the law of sines says that for a triangle such as this, where I have these opposite sides, I have this little c, which is the angle, big C, which is the side opposite it, and then little a, which is the angle, big A opposite that, and then what color should I use? Maybe pink. I have, whoa, that really didn't work. What about, will blue be better? I'm running out of colors, oh no. What about red? Is red gonna, red actually is the best one. It's not pretty, but I think that's the best we can do. Okay, little b is the side, and little b is the angle, and big B is the side. So we have these sides across from their corresponding angles, and the law of sines tells us that the ratio of the sine of these angles to the opposite side always has to be the same. So it tells us that sine of A divided by A is equal to sine of B divided by B is equal to sine of C divided by C. Also, of course, if we take reciprocals, this equality will hold. It will maintain itself. You might have seen this written as A over sine of A is equal to B over sine of B, which is equal to C over sine of C, sine of little c. And maybe I can do that B a little bit nicer here. There we go. So that's it. Before we prove it, what is it used for? How could we use this? Well, suppose I have a triangle, a non-right triangle, and let's say in green I have some known quantities. Suppose I have little a and I have big A, and then I have little b. And suppose I want to fill in the rest of this triangle. Suppose I want to solve for this unknown quantity, big B. Can I do that? Well, law of sines says that's actually pretty easy. The law of sines says that big B divided by sine of little b is equal to big A divided by sine of little a. This allows me to solve for b. I can say big B is sine of little b divided by sine of a times a. And since these were all known quantities, I know that, and I know that, and I know that, so a was known, therefore sine of a is known, b is known, therefore sine of b is known. This allows me to solve for the thing that I was looking for. Same thing if, let me just do one more of these and then we'll get to the proof. Same thing if I was missing an angle. If I was missing, say, let's call this little c is unknown, but big C is known, and big B is known, and little b is known. Well, if I want to solve for little c, well, I know that sine of little c divided by big C is equal to sine of little b divided by big B. So I can solve for sine of c. Sine of c is equal to big C over big B times sine of little b. And since again, little b is known, sine of little b is known, big C is known, so big C is known, and also big B is known. So that allows us to solve for sine of little c, and then I can get c by taking sine inverse or arc sine. I'll write both because different instructors use different notations. C is going to be sine inverse of c over b, or arc sine of c over b times sine of little b. And there's a little bit of a subtlety with this. Whenever you take the arc sine or the sine inverse of something, whenever you do the inverse trig functions, you have to think about getting several solutions. What's going to come out of a calculator if you do that? If you're doing special angles, it's different with exact values. But whenever you plug these things into a calculator, there's a little bit more to think about. We're not going to go into this in detail here. Please do take a look though at the videos on sine inverse, and if you're interested in the law of cosines, the cosine inverse function for the subtleties. But I don't want to get those are important to know about. I just don't want to get sidetracked on that here. I want to get to the proof. But this is how you use it. This is how we can find the missing sides and angles in a triangle. We can use this along with the law of cosines, either this or the law of cosines or a combination of them to solve triangles. So that's very nice. That's terrific. But how do we prove it? Suppose you're like, okay, that's nice to know that, but how do I know that it's true? And you should always be asking yourself that. Never just take anything on faith. We need to be able to prove and derive absolutely everything. That's how we do really, really well in math, and also learn properly. But most people just want grades. That is how you get the good grades, if that's your primary concern. So okay, let's take a look at the proof. This is A, this is little a, this is just keep the colors the same. It doesn't matter. That's B, that's little b, and then this will be C and little c. Did I write C? What is going on? There we go. B and little b, C and little c. Okay, all the letters are what they're supposed to be. Terrific. Okay, so I'm going to prove this for A and C, and leave proving the rest of it for B. So getting B in there and sine B as an exercise, because it's the exact same way of proving it. You just sort of reorient the triangle, and I think that's a great exercise. Always, I know I say this every time, but always it's a great idea at the end of these videos to either do it as you're following along, stop the video and try to anticipate what I'm going to do and work through it, or work through it yourself afterwards, or when you're done, stop it and make sure you can go through and recreate all the stuff that I've done in the video. That's the way to know that you really understand it. So how am I going to prove this? Well, as I mentioned at the beginning, I'm going to use this really, really useful and important trick, which is I'm going to draw in a right angle here. Now, there's no right angles in this triangle, but I can take any of the vertices, any of the tips of the triangle, and connect it to the opposite side at a right angle. And all of a sudden now, I get a right angle, and I can use the Pythagorean theorem. Okay, sticking right angles into stuff, whether it's triangles or circles or squares or any shape, all of a sudden you get to use sine and cos and tan and the Pythagorean theorem. So really useful trick that doesn't go away. You'll be using this well into university. Okay. So and as soon as I do something like this, as soon as I draw a new line into the diagram, I immediately want to assign a variable to it, assign a letter to this. I'm going to call this side D, because now I can do calculations with it. I also, because I've broken up that side B, I'm going to label the bits. That is B1 and that is B2, the pieces that I've broken B into. And now everything is labeled. I can start with the proof. And as I said also in the cosine proof video, the way that we do this is because people have a lot of trouble getting started with proofs, I just start computing the quantities that I'm interested in. Here I'm going to be trying to show that, and let me get back to my neutral computing color here, that sine A over A is equal to sine of C over C. Right? And I picked A and C because when I connect that vertex at little b to the side big B, well, that lets me compute the sines and cosines of little c and little a. So I'm forgetting about b for now. And then again connecting b, getting that final piece, which is equal to sine b over big B. We're going to leave that as an exercise. We're just going to do this bit. So how do I start? If I'm worried about this, I don't just stare at it. I actually start computing these things. What is sine of A? Sine of A is D divided by V2. That's great. What is happening? Sine of C is equal to D over B1. So that's terrific. What is then sine of sine of little a over A? This is D divided by B2 divided by A, which when I divide by something, it's like multiplying by the reciprocal. This is D times A divided by B2. That's what sine of little a divided by A is. What about sine of little c over C? Well, this I've just found out is equal to D over B1 divided by C. So same thing, I multiply by the reciprocal, and I get D times C divided by B1. And I'm just realizing I made this a capital, so let me just fix that. This is supposed to be little b2 and little b2 over there, just in case everyone was confused by that. Hopefully it wasn't too disorienting. Okay, so I get sine of little c over C is D times C over B1, and I get sine of little a over A is D times A divided by B2. And so now where do I go from here? Well, I reevaluate. I say, all right, D times A over little b2 is going to be equal to D times C over little b1 if and only if I can cancel the d's and say A over b2 is equal to C over b1. This is a great way to think your way through proofs, right? If you want two things to be equal and you are trying to prove this, well, think about what would you need to be true in order for them to be equal. If it's true, that thing has to be true. So you set them equal and see what needs to be equal in order for this to happen, and then figure out why that's equal. If you at this level at least, if you're doing proofs right, they're going to prove themselves. If you just avoid that trap of staring at the page and actually write down the things that you're looking for and remember what you're doing, remember what you're trying to prove, because it's very easy to forget as when you get lost in the computations. They actually just kind of work themselves out. Okay, so this is what I need. I need A divided by B2 to be equal to C divided by B1. And A is this side of the triangle, and C is that side of the triangle. Great, okay. And when is this going to be true? Well, this is going to be true exactly when A times B1 is equal to C times B2. I can just cross multiply by B1 and by b2. And so now I need to think, did I fucking fuck up the proof? What's wrong with me?